Year 13, Chapter 8, Trigonometric Identities, Lesson 2, Double Angle Formulae. So, we're going to derive the first of the double angle formulae, another set of very useful trigonometric identities. We're going to start by using the compound angle formula that we previously derived for sine A plus B. It's at the top of the screen, so you've got this for reference. Now, I'm going to let angle A equal angle B. So this means that wherever there is a B, I can replace it with an A. So the identity then takes this shape, with every B replaced by an A. I can now simplify this. Sine of A plus A is sine 2A. And look at the right-hand side. Can you see that this and this are both the same term? And they can both be written as combined as 2 sine A cos A. So here we have the first of the double angle formulae, or the first of the double angle identities. Sine 2A is equivalent to 2 sine A cos A. Now, why is it called a double angle formula? Because of the 2A here. So we're now going to use a different identity. We're going to use cos of A plus B this time, which we know is equivalent to cos A cos B minus sine A sine B. You have to be a little bit more careful with the cosine compound angle formulae. So again, we're going to let A equal B. So everywhere there is a B, I will replace it with an A. Now, this then gives me cos A plus A is equivalent to cos A minus sine A sine A. So what does this give me? This results in cos 2A is equivalent to cos squared A minus sine squared A, which is another double angle formula, but this time for cos 2A. Now, let's consider this identity cos 2A is equivalent to cos squared A minus sine squared A in a little bit more detail, because of course we know that sine squared theta plus cos squared theta is equivalent to 1. And we can make use of that identity. So our Pythagorean identity here tells me that cos squared A must be equivalent to 1 minus sine squared A. And what I'm going to do is replace cos squared A with 1 minus sine squared A. So this now tells me that cos 2A is equivalent to 1 minus sine squared A minus sine squared A. Now, look at these two parts here. We can simplify this, can't we? We now get cos 2A is equivalent to 1 minus 2 sine squared A. And this is another form of the cos 2A identity, a really useful form, as you will discover. Now, furthermore, we know that our Pythagorean identity allows us to say that sine squared A is equivalent to 1 minus cos squared A. And I'm now going to take this identity here and I'm going to replace sine squared A with 1 minus cos squared A. I could go back to the beginning and do it with this identity here as well. It would amount to the same result. So this then gives me cos 2A is equivalent to 1 minus 2 brackets, and instead of sine squared A, I'm going to put in 1 minus cos squared A. What does this then give me? Cos 2A is equivalent to 1 minus 2 plus 2 cos squared A, expanding the bracket, and this then leads to the third form of the double angle identity for cos 2a, which is 2 cos squared a minus 1. So there are three forms of the identity for cos 2a. This one here, which we derived originally, and these two versions here, which can be derived from that first version. Now, you either need to memorise all three versions, know that they exist, or know how to convert one into one of the others. I personally think it's better to try and memorise as many identities as possible, even if they're given to you in the formula booklet. If you know them, and you know them off by heart, you will have them at your fingertips, and it will save you a lot of time trying to look things up. It also means if you know them off by heart, you're much more likely to recognise them and be able to use them in questions. So, having identified a double angle formula for cosine and for sine, we're going to do this for tan as well. So here's the compound angle formula for tan, and as we've done in the previous examples, let's let A equal B. So everywhere there's a B, I'm going to replace it with an A. So let's see what we get. So I end up with tan A plus A is equivalent to tan A plus tan A all over 1 minus tan A multiplied by tan A. And this simplifies very neatly to give me tan 2A is equivalent to 2 tan A in the numerator, all over 1 minus tan squared A. And here is the third of our double angle formulae. So we'll finish off by summarising the three double angle formulae identities. Sine 2 theta is equivalent to sine theta cos theta. Cos 2 theta is equivalent to cos squared theta minus sine squared theta. It is also equivalent to 2 cos squared theta minus 1, and it is also equivalent to 1 minus 2 sine squared theta. So remember, there's three versions of the cos double angle formula. And finally, tan 2 theta is equivalent to tan theta over a denominator of 1 minus tan squared theta. So again, these formulae may appear in formula booklets, but the better acquainted you are with them, the more success you will have at solving questions and problems efficiently, because you will be able to draw on your knowledge of these without having to look them up. Memorising them also means you will recognise when you need to use them in a question without, again, having to waste time looking them up. So we're going to have a look at three examples where we make use of the double angle formulae. The first one involves solving a trigonometric equation. So we are going to solve the equation sine 2 theta equals 2 cos theta for theta between 0 and 2 pi. So as soon as we see sine 2 theta, we know we can make use of the identity 2 sine theta cos theta. Now, do not divide by cos theta. It will disappear, and then you will lose solutions as a result. So as ever in these situations, you need to subtract and then factorise. So we have 2 sine theta cos theta minus 2 cos theta equals 0. We can divide through by 2. That's just a numerical factor here. And then factorise cos theta. So we then have sine theta minus 1 equals 0. So that is the key to solving these questions, and you've seen these sorts of equations previously. Now, from here, we can then identify that either cos theta equals 0, which will lead to some potential answers, or sine theta must equal 1, which will lead to other possibilities. Now, cos theta equals 0, we can see instantly from the cosine graph that theta has to equal pi by 2, or theta has to equal 3 pi by 2. Now, sine theta equals 1, that then gives us a repeat solution of theta equals pi by 2. So the answers for this particular question are theta equals pi by 2 and 3 pi by 2. Let's look at another trigonometric equation. We are going to solve the equation cos 2 theta equals -2 minus sine theta. And we will do this for theta between 0 and 2 pi. Now, we know that we can't easily solve equations which have a mixture of sines and cosines unless they factorise neatly, like in the previous example, and we've dealt with similar situations which involve cos squared and sine squared. Now, the trick here is we must choose the correct identity for cos 2 theta. And as you can see, there are 3 possibilities. Now, we know from previous work we've done on solving trigonometric equations that we can solve equations that involve sine squared and sine, but we can't if it's a cos squared and a sine, or a sine squared and a cos. We can't have mixed up terms. So that then tells me that I would rule out this. I don't want to replace cos 2 theta with this because then I'd have an equation that mixed up cos squared, sine squared and sine. I don't want to use this either because then I'll end up with an equation that features cos squared and sine. But if I use this, that's fine because this will result in, if I replace cos 2 theta with this, 1 minus 2 sine squared theta is equal to -2 minus sine theta. So the equation only features sine. Now, we do need to rearrange this, so it's set equal to 0. So this gives me 2 sine squared theta minus sine theta minus 3 equals 0. And we have that quadratic style equation, which we can factorise. So this is going to give me 2 sine theta and sine theta in my brackets. I think we're going to have a 1 here and a 3 here. And I think this is going to have to be positive and this is negative. And always expand back to check that you have done the factorisation correctly. Now we have a pair of brackets which show 2 factors multiplying together to give us 0. So either sine theta equals 3 over 2, which is not possible. So we have no real roots from that. Or the other option, sine theta equals -1. Now, for the range of theta values that we've been given up here, this doesn't lead to anything more than one answer, which is theta equals 3 pi by 2. Now, the last example that we're going to do involves proving a trigonometric identity. Again, we've done lots of examples of this in the previous trigonometric topic, and it's important that we can see how to do this when it might perhaps involve double angle formulae as well. Now, we need to choose the more complex looking side, which is definitely the left-hand side here. So the left-hand side is equivalent to 1 minus tan squared theta over 1 plus tan squared theta. Now, I am aware that there is an identity that we have used previously, whereby we know that 1 plus tan squared theta is equivalent to sec squared theta. We learned about that previously. It's one of the 3 Pythagorean identities. So we can replace the denominator with sec squared theta. But what is sec squared theta? It's 1 over cos squared theta. So effectively here we have 1 minus tan squared theta divided by sec squared theta, which is 1 minus tan squared theta divided by 1 over cos squared theta. And of course, thinking about how we work with fractions, we can replace that with multiply by cos squared theta. It's always tricky when there's a reciprocal trig function in a denominator. We get this effect here. Now, I'm going to rewrite tan squared theta as sine squared theta over cos squared theta, and then expand. So this then gives me 1 multiplied by cos squared theta, and then when we multiply these parts together, can you see cos squared theta cancels, leaving me with sine squared theta. But what do we know? We know that cos squared theta minus sine squared theta is cos 2 theta. It's a double angle result. So we get to the right-hand side.